First we begin with the reference books, and I told you that this is the one reference book which I prefer, and the other one is this two elsewhere. Okay, and as I told you that CFD is a very vast subject. None of these books is actually covering all the topics together, right? And therefore you will find some topics in some books, some topics in some other books, like so. All these books are useful, but again, in this course it will not be possible to take up all these books. Okay, so okay, now we talk about what is a computational fluid dynamics. Computational fluid dynamics, CFD, as you know, is called, full form is computational fluid dynamics. Now it's a branch of science that is used to solve problem of fluid dynamics by numerical methods. So two things are specific about it. One is fluid dynamics and the second is numerical methods, and that is coming from the word computational. Okay. Now what is a fluid mechanics? Fluid mechanics basically stipulates laws of physics that govern the fluid motion. So what we have, fluid mechanics is telling us certain laws which actually govern the fluid motion. Now what are those laws? First one of them is conservation of mass, which actually gives you continuity equation, which is one and same thing. The equation which you write using conservation of mass is called continuity equation. Then you have Newton's second law of motion. Now when you apply this equation, what you get is conservation of momentum. Now there are three equations for conservation of momentum, because momentum is a vector. Okay, so you have three direction, x, y, z. You will get three different equations. Now here we must remember one thing, that we are talking about classical mechanics, or a mechanics in which the velocities are not high, right? So to the extent we want the details, Newton's law are sufficient for us. Otherwise, you know that high speed Newton's law are not valid. You have to go for Einstein's relativity. But because we are dealing with day-to-day motion, right, or we can say classical mechanics, we can use these laws. Then again you have one more law, that is a conservation of energy, which gives you energy equation. Now again here also, because our fluid motion will not involve nuclear reactions, right, so we can easily use conservation of energy equation. Suppose there are problems which are dealing with nuclear reactions, and if you want to apply mechanics there, fluid mechanics, then you have to take into account the equation E is equal to mc square. Okay, those conversion equations will come in, and then these equations of, you can say, energy equation would change. Okay. Now apart from these laws, what you find is there are other engineering laws or equation that govern the fluid flow. Okay. The first one of them is equation of state, or you have other thermodynamic relations. So if you look at thermodynamics, there are a number of equations there. Okay, equation of continuity equation and energy equation, they are part of thermodynamics, but there are many other equations also. Second law, first law is conservation of energy, the second law that will come into play, and even the equation of state, if the gases are there, PV is equal to nRT, that is the one equation is there. Then you have also these Maxwell equations, right? They are also part of it. So all these equations are part of it. Then laws of heat transfer, they will also come into play. You have conduction, convection and radiation. All these equations will come into play. Then laws of diffusion, I told you that whenever there are different species in the domain, they exchange. Then the concentration doesn't remain uniform. What is diffusion? There are two different species. One is moving from one place to another, that is the diffusion process, okay? And it depends. If in your system there are, even if there are multiple species and there is no movement, intermixing or the change in concentration, you can take it as a single species, right? So it depends, you have to decide. Like in case of room, if you are talking about temperature and you are concerned only about temperature, you can talk about it as a air as a single species. But if you are talking about the concentration of carbon dioxide, right, then you have to take it as multiple species. And you have to also take into account the diffusion equations. So it depends what is the objective and what is the type of problem before you, right? Then chemical equations, now which govern the chemical reactions. Now if there are chemical reactions, and chemical reactions we know that when different type of molecules combine and produce different other molecules. So let me check if I can. Now if you see this chemical reactions, I was telling you that if you have A plus B and that gives you C plus D, right? And I have put two arrows here, forward and reverse, because chemical reactions occur in both the directions. Chemical reactions occur in both the direction, forward as well as backward. Now what is happening? A plus B are combining and getting converted into C and D. So what will happen? Your concentration of A will go down, concentration of B will go down, concentration of C will increase and concentration of D will also increase. This is what will happen. So diffusion will also come into play and the chemical reaction will also come into play. All these things will take place and we have to take care of that. Okay? Now, so you have to take care of those chemical equations which are which govern the chemical reactions. Okay. Now, when we talk about these laws, many of these laws are having partial differential equation. They have the form of partial differential form, okay? And they actually come into play. So your equations can be both algebraic equations as well as differential equation. The partial differential equation as well as algebraic. So you can say algebraic equations, comma partial differential equations. Both of them will come into play. They govern your fluid. So this is your fluid mechanics plus heat transfer plus thermodynamics, right? Plus chemical reactions, all that will come into play. Now then you move on to the mathematics. Now we have to actually solve these equations. Now the role of mathematics is to solve this equation. Why the mathematics is coming here? Because we have to solve these equations. Now there are two methods. One is called analytical method. The second is called numerical method, by which you solve these equations. Okay. Now you find that your governing equations are normally in differential forms, and in most cases analytical solutions cannot be attained. The problem is that we are unable to find the analytical solutions to differential equation, and that we have seen also in our younger classes, that whenever we solve a differential equation, right, only very few equations can be solved, and if there are multiple equations coming together and they are coupled, it becomes much more difficult. Okay, so even if analytical solution is one possibility, it is actually not available to us. Okay, so then we have to resort to numerical methods. Okay, now to solve these differential equations, you have to discretize the domain as well as the equation. What we have to do is, I was telling you that you have to discretize the thing, numerical solution. Now what is happening? Discretization means that you have a domain, so you have a domain like this. Okay, now you have to discretize it. What does that mean? You have to okay, and so on. You will keep on dividing it. Even otherwise also there can be a thing like this. And you can divide it like this. Something. Okay. This is called discretizing the domain. You break it into smaller parts. Okay. Now then there is also discretization at the level of the equation. That means if you have a differential equation in the form, let us say del y by del x, right, plus c, you can say c or equal to 0. If you discretize it, it becomes del y by del x plus c to 0. right? So this is what you are doing in the whole process. Okay, coming back to this. Now, discretization process involves dividing the space and time continuum into large number of cells. So you divide the space and you also convert the equation into this algebraic form. Okay. Now, then what happens, the equations governing the fluid flow are now applied to the cells individually. So now what is happening? All these equations which you have written, maybe 7, 8, 9 or 10 equations, they are applied to each cell individually. Now your domain is divided. So you will write for it. Now then what happens? Variables forming these equations are present in most of the equations written for a cell. Now, these variables are actually there in most of the equations. Then whatever also happens, that when you write a cell containing variables, when you discretize the equation, then actually you have to take the value of the adjacent cell. So while you are writing equation for cell A, you are taking the value of parameters from cell B, right? Let us see what happens here. Suppose you are writing this. Now del y by del y, when del y by del x, when you write it is equal to actually y2 minus y1 divided by x2 minus x1. So y1 comma your x1 comma y1, they represent cell 1, and x2 comma y2, they represent cell 2. So what is happening is, when you write equation for a cell, you are taking the help of adjacent cell. Okay. So now as a result, these equations become coupled. They have to be solved simultaneously, because now if you want to solve the equation, any equation, what will happen? It will have variable for the adjacent. Now you have to solve that also. So you have to take that cell. Similarly, for solving this variable from the second cell, you have to take the third cell, and then from the fourth cell, and so on. So as I told you last time, that if you have equations like this, uncoupled equations, uncoupled equations are why 2x plus 5 is equal to 0. You can simply solve it irrespective of what is the second equation. You will get x is equal to minus 2.5. The second equation is y minus 10 equal to 0. You simply get y is equal to 10. These are uncoupled equations. Because to solve any parameter, one equation is sufficient. You don't have to go for another equation. But now take a case where you have 2x plus 3y is equal to 5 and 2x minus 3y is equal to minus 1. These equations cannot be solved independently. They have to be solved together. So this becomes a coupled equation. What does it mean? That when you are talking about these equations, now each cell is having 8 or 10 equations, right? and those equations, because they are differential, so you have to take the help of the additional adjacent cell, so they are connected, and similarly each one of them connected. So you get, if your problem contains suppose 1 million cell, right, you will have, let us say each cell has 8 equations, you have 8 million equations, right, and all these are connected and they have to be solved together. So, and this is a humongous problem, you cannot solve it easily. Because you know that solving a 3 by 3 matrix is how difficult it is. Even computers, if you go for 10 by 10 matrix, they will take a lot of time. They start this, the algorithm we have to solve this equation becomes very, very complicated, very, very slow. Okay. But so even if you have the advanced computers, the solutions to these equations are not possible in reasonable time frame. But fortunately, they are the special type of equations. These equations are called sparsely populated equation. Right? They are called sparsely populated equation, they are called. What does that mean? That even when you are having 8 million variables, now you are actually dealing with 8 million variables, 8 variables for each cell. But what happens? Each equation is containing 8 million variables. Okay? But in each equation, only the neighboring cells are relevant. So, if there are 6 cells, 6 sides, if you are having a 3-dimensional case, you have 6 cells, left, right, top, bottom, front and back. So, you have only these variables coming into play. So, even if there are 8 million variables, you have 8 into 6 variables in one equation, maximum. Because you are talking in terms of only the adjacent cell. So, for a given cell, you will get variables only from the adjacent cell. So, even if any equation contains, in actual thing, all the equation will not contain all variables. There are 8 equations we are assuming, fluid mechanics equation, right? So, there will be 8 variables, right? So, each equation may not contain all the 8. Let us assume that each equation contains all the 8. Then when you write an equation and each term is a differential, then you will take the adjacent one. So, how many variables you can get? 8 into 6, 48 variables and the center one 56, total 56 variables will be there. Remaining 8 million variables are 0. So, these are called sparsely populated matrices, and people have developed technique to solve that. Okay, and that is why mathematics come into picture. Right? If you have to solve all these equations simultaneously, and if the equations are of the order 10 by 10 or 15 by 15, maybe 50 by 50, you don't need mathematics, you already know that mathematics. You use a good computer and everything is solved. But now the problem is that The methodology which we already have, that of solving the equations simultaneously, will not work because there are 8 million equations. But fortunately, these equations are sparsely populated. Most of the terms are 0 and only few terms are significant. So the techniques have been developed to solve these equations, and that is where mathematics come into picture. Okay? CFD में तो they are always there. CFD में तो सिंपल सी थिंग है ना, देखो आपका जो टोटल मैट्रिक्स बनेगी उसमें if I can show it on a diagram. Suppose you have you write one equation here, ठीक है, and the variables are x1 a1 x1 plus a2 x2 plus and so on equal to B1. Now if you are talking about this, if this is your cell, 3 number is the cell, okay, this becomes significant to you and this becomes significant to you, right? And these all terms will be 0. Right? So the equation has 8 million variables, no problem, but coefficients of all of them are 0 except for few. Okay? So that is why it is called sparsely populated. Now, when you are solving this sparsely populated matrix, again there is no direct method. You have approximations. So you develop techniques, right? The real technique which is 100% sure, correct, that is Gauss elimination method. Matrix you solve one by one, that is what we know. And once we get the solution, it is final. But that process is, very, very long. So you make approximations. Once you are making approximations, then another responsibility comes on you, that you are actually reaching the actual solution. So what is required is not only that you should have the methodology to solve such equations, but also to ensure that you are getting the correct solution, because you are going by an approximate method. As far as Gauss elimination method is concerned, we know that we get the correct solution, right? Because it's all logical, right? So everything is connected. You know where you are leaving the path, right? It is suppose like you are walking on a road, right? And some marks are put on that road. So you have to move from place 1 to place B, right? You are following those marks. You will start from A, reach B. Now assume that there is no path from A to B. You just have an idea that B is at this point in this line, and you start moving randomly, or some a hunch feeling that if I go like this, I will go there, this and that. Then you finally, when you reach the end point, and if you think that you have reached the point, how would you know that you have actually reached the right point? because you have not seen that point. Which means that all your deviation, all the approximation which you made should nullify each other in the final analysis. Okay. Either you have a self-correcting mechanism that whenever you leave the path, you know that okay, I have deviated, I can come back. But if you don't have a pole star, if you don't know where you are going, you don't know the final solution, you have to be sure that you have reached the right solution. So that has to be built into that mathematics. Okay, so you are entering in a different type of mathematics. Discretizing the equations was not difficult. That already exists, Taylor series already exists. Solving the matrix is not difficult, it already exists, method already exists. Now a new mathematics is coming up that which is telling you how to solve sparsely populated matrices and make approximations so that you reach faster and ensure that you are not making error. This is a new type of mathematics which has come in. Okay, so that is why it comes in. And then we talk about this computer science. Okay, so you have seen that we have a physics, and fluid is such case where all types of equations come into play, right? In the next lecture we will take up those equations, that what are those equations which we have to deal with. There are many of them. I'll be listing around 20 equations before you, right? So that is physics. Then mathematics we have talked about. Now we enter the computer science part of it. Now again, why the computer science becomes important? Because there is a, you can say, tug of war between computer science and mathematics. Mathematics is trying to get the solution fastest possible, and the computer science is telling, computer is telling that I have a limit, I cannot go faster than this, I cannot take more number of variables than this. So then mathematics has to come for the help again. Okay, let us bypass this problem like this. So it's something like that, the resources which you have are not adequate, that you cannot play freely, right? It's something like that, you go to the market, right? You have some agenda with you, you have some limited money, you have to make many combinations. Oh, I buy this one, or maybe not this one, maybe this cheaper one, or this costly one, or maybe I postpone this buy. You have to make so many decisions because the amount of money available to you is limited. Same thing is coming here. The computer is telling that I cannot go beyond this limit. So the person who is operating it, he has to think about what is the way out. How can I circumvent this limitation? How can I overcome these limitations? That has to be done with the help of, you can say, mathematics, because computer is mathematics, mainly mathematics, and slightly different, a different type of mathematics is there, Boolean mathematics is there, binary system is there, whatever else is there, logics are there. Computer is what? All the mathematics plus hardware, right? So that how to develop that program, that can use the limited resources. And what the computer fellow is thinking, that how can I increase the RAM, how can I increase the CPU speed, so that I give more freedom to this person, he doesn't have to, he can do it faster, okay, something like that. So we know that we have to use computers, there is no doubt about it. Then the size of problem is so large that even advanced computers cannot handle. We also know that. So then you have to develop new algorithms to solve the problem. Now, why new algorithms? Now, because you are going approximation. If you are going a fixed technique, suppose you have a absolute sure technique, there will be 2, 3, 4 types of approaches, right? But when you are making approximations, there can be hundreds and hundreds of them approaches. So you have to think of those algorithms. Then on the other side, you have to talk about size and speed of RAM and speed of CPU. These things become important, and time available to solve the problem. So there is a tug of war going between. The scientist is saying, okay, I simplify the problem. Mathematics are saying, okay, I find a different technique to solve it. The computer people is saying that, okay, I increase the size of the computer and the speed of the computer so that we can solve bigger and bigger problem. Okay. Now further, I told you that these calculations have to be carried out repeatedly, which means truncation error becomes part of it. There are 2 types of error I talked about. One was truncation error, and the second was round off error. Truncation error is part of algorithm, you can say mathematics. Round off error is part of computer. Part of computer limitation, okay. So you have to take care of both. So in turn, what we come to the conclusion that how we have to integrate fluid dynamics, mathematics and computer science, all the 3. And this integration is not a simple addition, that you don't bring 3 people together and okay, we'll solve the problem. Each one of them has to consider the problem of the other and develop accordingly. So they have to interact with each other, understand each other's limitation and try to solve it jointly. So this becomes this type of exercise. All the 3 disciplines operate at their extremes, I said, and this makes CFD a specialized subject. And although CFD is an integration of 3 branches of engineering, please note that only specific sections of mathematics and computer science are incorporated in CFD, while CFD in SS remains the extension of fluid dynamics. So CFD is actually fluid dynamics only, but it involves mathematics and computer science rigorously. Okay, and so we can put a diagram like this. CFD is, you have, this is what the CFD is. It is made up of these 3 things: fluid dynamics, computer science and mathematics. Okay, and we will continue from here. And okay, so then we will see that there are what are the equations. Basically, let me just see that what all will be view. Okay, only one section we have completed. We will talk about many things, that what are the different approaches to solve the problem of fluid mechanics. We will talk about that. And there are three types of approaches. One is experimental, analytical, and CFD. What is the relative advantages and disadvantages of the two? Then basically what are the equations we have to deal with, and then what are the places where it is used, CFD. What is the scope of this, and what is the future of it. We'll talk about all these things. And okay, so